Hello everyone, I welcome you all in second lecture of module 3 under course mechanics of solids, and that module 3 is regarding bending stresses, shear stresses and torsion, and we are discussing part A of that, bending stresses. And in first lecture we have discussed about theory of pure bending, and we discussed about the equation of pure bending, that was M by I is equal to E divided by R is equal to sigma divided by Y. So in that equation, M stands for bending moment due to external forces, I stands for moment of inertia, then sigma stands for stress getting developed due to bending moment, and Y is the point distance from the neutral axis, and E is Young's modulus, and R is the radius of curvature. So with that, again we discussed in lecture that simple numerical regarding how to go for analysis of bending stresses, and we discussed about standard cases about the maximum bending moment due to those forces. But in other cases, you need to go for calculation of maximum bending moment as per the methodology what we have discussed in module 2, that was SFD and BMD. So this lecture will be going for discussion of two more numerical regarding bending stresses. The statement of the numerical of this second numerical is something like this. A simply supported beam AB of span 6 meter carries 2 point loads 50 kilonewton each at 2 meter and 4 meter from left support. The cross section of the beam is T section with top flange 100 mm by 50 mm and web 150 by 40 mm. It is asked that analyze the beam and find maximum bending moment and draw a flexural stress distribution diagram at that section. So you have to find out first of all the maximum bending moment and then find the stresses getting developed due to that bending moment at that particular section. So in this numerical, the diagram of the beam is not given, as also the cross section is that diagram of cross section is also not given. You have to develop those two diagrams. So part of solution, firstly we will be drawing the beam as discussed in the numerical. So it is a simply supported beam as drawn over here. At A it is say hinge support, at B it is say roller support, subjected to 50 kilonewton force at 2 meter from support A, and 50 kilonewton one more force point load at 4 meter from A, and the total span is 6 meter. So that is drawn, and then you have to draw that cross section. So cross section is said that top flange, it is T section with top flange 100 mm by 50 mm. So for flange, width is 100 and depth is 50, and in case of web it is 150 mm by 40 mm. So this 150 mm for web is its depth, and 40 mm is the dimension about its width. So with this diagram you need to go for further calculations. So as this is simply supported beam subjected to 2 point loads at the same distance from either of the supports. So the maximum bending moment will be at midspan at 3 meter from support A. So for further calculation you need to first of all find the reactions getting developed either at A or at B, and then consider that section at 3 meter from A and find the maximum bending moment. So if we apply summation of moments about B equal to 0, so that is equilibrium condition. So for this, if we take moments about B, now if VA is vertical reaction at A, the moment of that will be VA into 6, and for this 50 kilonewton force at 2 meter from B, that moment will become 50 into 2, and the another force, that is 50 kilonewton acting at 4 meter from B, that moment will be 50 into 4, and the reaction moment will be clockwise, and these two forces due to those movements are anticlockwise. So the equation is VA into 6 minus 50 into 2 minus 50 into 4 must be equal to 0. So VA will become 50 into 2 plus 50 into 4 divided by 6, and that gives us the reaction at A as 50 kN. So now if we go for calculating maximum bending moment at 3 meter from support A, so that gives us maximum bending moment as 50 is the reaction at A. So 50 into 3, that will be bending moment due to this reaction, and at the left of that point 3 meter from A, we have this point load 50 kN, and if we are taking moment about 3 meter from A, as that force is at 2 meter from A, then moment of that will become 50 into 1 at 3 meter from A. So 50 into 3 minus 50 into 1. So again this reaction is creating clockwise bending moment at that midspan, and this 50 kilonewton force is creating anticlockwise, so that is negative. So 50 into 3 minus 50 into 1, that gives us total bending moment as 100 kilonewton meter. That is maximum bending moment at 3 meter from support A. So now you need to calculate centroid of this complete T section. So what we can go for is you can consider one part, that flange, as one rectangle, one part of the cross section, and the another part of the cross section is that web as it is given. So to calculate the position of neutral axis, that is centroid, from bottom, applying y is equal to summation ai yi divided by summation a, or you might have used equation as y is equal to a1 y1 plus a2 y2 divided by a1 plus a2. So with that, if we consider the movement of areas about bottom, and from bottom we are calculating position of the neutral axis. So the equation becomes, for first area, if we consider flange, the area is 100 by 50 is the area of that flange, and its centroid will be at 50 divided by 2 from top. So from bottom it becomes 150 plus 25, so that is 175. So A1 is 100 into 50, and Y1 is this 175, and plus A2 Y2. So if we now consider web, area of web is 150 by 40 mm, so that is A2, and Y2 is its centroid from bottom, so that is 150 divided by 2, so that is 75. So A1 Y1 plus A2 Y2 is written, and divided by A1 plus A2. So A1 is 100 into 50 and A2 is 150 into 40. So if we calculate that, then it gives us this calculation as 120.45 millimeter from bottom. So that is the position of centroid of total T section from bottom, and then you can calculate what is the top position and bottom position. So Y bottom we have calculated as 120.45. So Y top, that can be calculated by deducting from total depth, that is 150 plus 50, that is 200 mm. So from 200 mm, if you deduct 120.45, the remaining is from neutral axis the distance of top position, and that distance is 79.55. So that is 200 minus 120.45. So with this calculation of Y bottom and Y top, you need to go for draw that neutral axis in the drawn T section. So that gives us the diagram as shown over here. So this is Y bottom, and that distance is 120.45 millimeter, and this is Y top. So that distance is from neutral axis 79.55 millimeter, and this is position of neutral axis from top and from bottom. So that you have to develop. Then you need to go for calculating the moment of inertia, and now that moment of inertia is about the neutral axis. So in earlier numerical, that cross section was rectangle, and we were aware that at cross section, if it is a rectangle, the centroid will be at the half of the depth of that rectangle, and that is the neutral axis. Now in this T section or I section, you need to calculate the position of the neutral axis, and again you need to calculate moment of inertia of complete section about the neutral axis, and then you need to go for using that parallel axis theorem. So using parallel axis theorem, that is I about neutral axis is equal to summation I of that particular part of that cross section about its own centroid, and then that A1 x1 square or AI xi square, that is its area of cross section, and that is distance between its own centroid from the neutral axis. So these two are parallel axis to each other. So that is parallel axis theorem. And if we use parallel axis theorem, now that will become I1. That if we consider this flange, top flange, that rectangle, it becomes BD cube by 12. Now B is 100 millimeter and D is 50 millimeter. So 100 into 50 cube divided by 12. That gives the moment of inertia of this flange about its own centroid, and the distance between its own centroid about neutral axis becomes 79.55 minus 25. So that is its centroid from top, and neutral axis from top is 79.55. So 79.55 minus 25, that gives us 54.55. So that is the distance between two parallel axes. So that gives us a moment of inertia of flange about neutral axis. Similarly, now if we consider a web and its own moment of inertia, that gives us 40 into 150 cube divided by 12. So that is BD cube by 12. And the centroid, its own centroid will be at half of 150, that is 75 mm from bottom. And from bottom, neutral axis is 120.45. So 120.45 minus 75, that gives us distance between neutral axis and centroid of that web portion. So that distance is 45.45. So if we write that complete equation and if we calculate it, that gives us the moment of inertia of complete T section about neutral axis, and that calculation is 39.564 into 10 to the power 6 millimeter to the power 4. So now with this, if we again go through these values what we have discussed earlier, so what we calculated is maximum bending moment, that is 100 kilonewton meter. Y bottom is 120.45 millimeter, that is calculated. Y top is 79.55 millimeter, that is calculated. And moment of inertia about neutral axis of complete T section is calculated, and that was 39.564 into 10 to the power 6 millimeter to the power 4. So using Flexural Formula, relation between that M by I is equal to sigma by Y is equal to E divided by R. And now if we are interested in finding what are the stresses getting developed, so that E divided by R is not required to be considered. So sigma is equal to M by I into Y. So that gives us, as the beam is simply supported. Now this is required to be considered. What is the case? If it is simply supported beam, the beam will be subjected to compression at top and tension at bottom. And if it is cantilever beam, it will be subjected to tension at top and compression at bottom. So that you need to consider. And then as the beam is simply supported, the tension will be at bottom. So sigma T, here T is used for tension. So sigma T is equal to M into, now Y will become Y bottom, tension is at bottom, divided by R. So now that is known to us that from neutral axis, bottommost position is 120.45 millimeter. So that is Y bottom. And the maximum bending moment, that was 100 into 10 to the power 6, divided by the complete moment of inertia, that is 39.564 into 10 to the power 6. So if you calculate that stress value, it gives sigma t, that is tensile stress, as 304.44 Newton per mm square. And instead of that, if we calculate at top what is the stress, that will be compressive stress. So that gives us, if we consider y top, that is 79.55 millimeter. So if we consider this in the calculation, then that gives us the maximum compressive stress at top as 201.06 Newton per mm square. So these are two values of the stresses calculated. At bottom it will be maximum tensile stress, that is 304.44 Newton per mm square, and at the top it is compressive stress, and that is 201.06 Newton per mm square. Now, knowing these two values, you can draw that bending stress distribution diagram, and that diagram will be something like this. So at bottom it is the tensile stress, that is 304.44 with some scale if you draw it, and at top it is compressive stress 201.06, and if you draw it to the scale, then if you draw this neutral axis at 79.55 millimeter from top, and this as 120.45 from bottom, then this will be inclined straight line, the variation of that bending stress from top up to bottom, and then this diagram is called as bending stress distribution diagram. So with this discussion, we will go for one more numerical in this lecture. So this numerical 3, the statement of the numerical is a cantilever beam AB of span 3 meter carries uniformly distributed load of 14 kilonewton per meter throughout the span. So it is 3 meter cantilever beam subjected to 14 kilonewton per meter uniformly distributed load over entire span, and a point load of 45 kilonewton at the free end. So one more force is there, a point load at the free end, which is 45 kilonewton. The cross section throughout the span of beam is I-section with the top flange as 200 by 50, bottom flange as 300 by 50, and the web 300 by 40 mm. And again, in general, it is asked that analyze the beam, find the maximum bending moment, and draw the flexural stress distribution diagram at that section. So again, the statement of the numerical is given, but the diagram as such is not given. You have to develop the diagram of the beam as well as the cross section. So as a part of solution, the first diagram, this figure is related to the force acting and the beam. So beam is cantilever beam, it is fixed at one support and free at the another support, subjected to 14 kilonewton per meter UDL over entire span, which is 3 meter, and point load 45 kilonewton at free end, that is there, and cross section is to be developed. So if it is I section, it is something like as shown in figure 6b, and what is said is top flange is 200 by 50. So this flange is 200 by 50, bottom flange is 300 by 50, so it is drawn over here, and then web is said as 300 by 40 mm. So this 300 for web is its depth, it is not width. So 300 by 40 mm, 40 mm is the width of web. So if we go further for the analysis of beam, as the beam is cantilever, the maximum bending moment will be at the fixed support. So it will be at support A, and you are aware that due to point load at free end, the bending value at fixed point is W into L, and due to UDL throughout, the bending moment at fixed support will be WL square divided by 2. So you can directly use that equation. So maximum bending moment will become 45 into 3, from that point load at 3 meter from support A, and for 14 kN per meter UDL, that will be 14 into 3, that is converted into point load, and its centroid will be at 1.5 meter from A. So that total calculation becomes 45 into 3 plus 14 into 3 into 1.5. So that gives total maximum bending moment at fixed support as 198 kilonewton meter, and it is hugging type of bending moment. So what we discussed in module 2, that in cantilever case it will be subjected to tension at top and compression at bottom, that is hugging bending moment. So to calculate the position of neutral axis from bottom, again as earlier in numerical 2 what we have calculated, similarly here for 3 different areas, by considering 3 different rectangles, you need to calculate the point of neutral axis from bottom. So if we consider first area, that is top flange, that is 200 by 50, and its centroid, so it is 300 plus 50, that is 350 plus 25, half of this 50. So that gives us 375 from bottom. So that is written in this equation, plus A2 Y2. Now if we consider A2 as a web portion, so that is 300 by 40, that is A2, area of that web, and its centroid will be at 150 from this position, or from bottom it will become half of 300 plus 50, so that becomes 200. So that is A2 Y2, 300 into 40 into 200, plus the third area, that is the bottom flange, its area is 300 into 50, that will be area, and Y3, that becomes half of this 50 from bottom, that is 25 mm. So that is A1 Y1 plus A2 Y2 plus A3 Y2 divided by now all area of that total I-section. So that will become A1 plus A2 plus A3, and if we calculate that value, it gives us this calculation as Y is equal to 176.35 millimeter from bottom, and from top from 400, if we deduct this 176.35, that gives us 223.65 as the distance of neutral axis from top. So if we go for drawing that diagram, that gives us this complete diagram of that I-section required for further calculations. So what we have calculated is position of neutral axis. So position of neutral axis from that top is 223.65. So that is distance of the neutral axis. Okay, so this position is neutral axis, and then from bottom it is 176.35. Now while calculating the moment of inertia of complete I-section about this neutral axis, about this particular position, so we need to calculate distances of its centroids of the part of the area of cross section about that neutral axis. So for example, if from top the neutral axis is at 223.65 and centroid of top area is from top, it is 25 mm. So if we deduct that from 223.65, that gives us 190.65. So that is distance between centroid of first area from neutral axis. Similarly, what is calculated is centroid of third area from neutral axis. So that distance is 151.35 millimeter, and web centroid is at 150 plus 50, that is 200 from bottom, and neutral axis is at 176.35 mm. So if you deduct from 200 176.35, then that distance gives 23.65 millimeter. So this is distance between centroid of web and neutral axis. So these calculations are required for calculating moment of inertia about neutral axis. So with this, if we go for using that parallel axis theorem, and if we consider the moment of inertia of individual areas, and if you convert it up to the neutral axis. Then for first area, that is top flange, its BD cube by 12 is written, so that is 200 into 50 cube divided by 12, and plus that AI xi, so that area is 200 by 50, and distance between on centroid of that area from neutral axis is 198.65. So that is written 198.65 square. Similarly, for second part, that is web position, that is the width is 40 and depth is 300. So that becomes 40 into 300 cube divided by 12, that is BD cube by 12. Its own moment of inertia about its own centroid, and neutral axis is at 23.65 mm from its own centroid. So that is converted to moment of inertia about neutral axis, that is 300 into 40 its own area into 23.65 square. So that is distance between those two parallel axes. Similarly, for third area, that gives us 300 into 50 cube divided by 12. So that is B is 300, D is 50, and then BD cube by 12 is its moment of inertia about its own centroid, and it is to be converted up to neutral axis. So that is 300 into 50 into, now those distances between two axes is 151.35. So it is multiplied with 151.35 square. So if you calculate this complete calculations, then it gives us moment of inertia of entire I-section about neutral axis, and that gives us 840.14 into 10 to the power 6 millimeter to the power 4. So with these calculations, now you can go for calculating the stresses at the top and stresses at bottom. So what we have calculated up till now is maximum bending moment is 198 kilonewton meter, Y bottom, that is bottommost position from neutral axis, is 176.35 millimeter, Y top is 223.65 millimeter, and the moment of inertia of complete I section about neutral axis is 840.14 into 10 to the power 6 in millimeter to the power 4. So if you go for that Flexural formula, M by I is equal to sigma by Y, as the beam is cantilever that we have discussed earlier, tensile stress will be at top and compressive stress will be at bottom. That is subjected to hugging type of bending moment. So sigma C, that is compression at bottom. So sigma C becomes M into Y bottom divided by I. So Y bottom is 176.35. That 198, it is in kilonewton meter. So that is converted into Newton mm by multiplying it by 10 to the power 6 and divided by that moment of inertia, that is already written. And then if you calculate this, that value, the maximum compressive stress at the bottom, that gives us 41.56 Newton per millimeter square. And similarly, if you go for calculating the tensile stress, maximum tensile stress, that will be at top. So that will be M into Y top divided by I. Now that Y top is 223.65. So that calculation gives us the maximum tensile stress at top is 52.71 Newton per mm square. Try to understand that capital T is regarding tension, and that C is related with compression, and it is not that at compressive it is Y bottom. You need to consider what is the case, whether it is simply supported beam or it is cantilever beam. If it is simply supported beam, the compression will be at top, and in case of cantilever beam, the compressive stresses will be at bottom. So that you need to consider while analyzing that numerical. So with these calculations, you can now develop flexural stress distribution diagram, and that will be something as shown in this figure. So that neutral axis is drawn, and distances of top and bottom are drawn initially to 23.65 and 176.35 millimeter. and at that point, at top, it is subjected to tensile stress of 52.71 Newton per mm square, and at bottom it is subjected to compression. It is 41.56 Newton per millimeter square. And then this, after drawing this to certain scale, if you this variation of that bending stresses from top up to bottom, that will be inclined straight line. So that is giving us maximum tensile stress at top as 52.71 and maximum compressive stress at bottom as 41.56 Newton per mm square. So this diagram is bending stress distribution diagram. This is required for the analysis. So with these two numerical, we are concluding this lecture, and I am thankful to you all for this lecture. Thank you.